Hi, welcome back to Free Energy Functions in Physical Chemistry. My name is Kevin Tokoph. Make sure to like the video and subscribe to the channel for future videos and notifications. This is another Gibbs energy transformation that we can do, and it quantifies not the temperature dependence, but the pressure dependence of Gibbs energy. In another video, we looked at the basics of Maxwell relations in thermodynamics, and one thing we discovered was that the volume is equal to the change in free energy with respect to pressure at constant temperature. Okay. Now, one thing we can also show, and I won't go into the heavy-duty mechanics behind this, but if we look at instead for the Maxwell relation a change in volume instead of just an absolute volume, then what we do to throw in this delta notation for a change in volume, for the free energy, we have to throw in a change there within the differential in the numerator. So now we have the change in volume is equal to the partial derivative of the change in free energy with respect to pressure at constant temperature. All right? And that relationship is again shown right here. All right? Now, again, like a lot of these transformations that come from Maxwell relations, this one is a separable ordinary differential equation. Now, delta V does not seem like it doesn't have a pressure in it, but remember from an ideal gas perspective, remember that volume can be written as nRT over P, and with other equations of state, it's not that simple, but volume is still a function of pressure. So technically right now, all of the pressure terms are on this side of the equation. There's no pressure terms on this side other than the actual differential. So what I'm going to do is I'm going to multiply both sides by dP. That cancels this and puts the dP over on the side with the function that is a function of pressure, meaning the volume or the delta V. All right? So there's that. Now what I have essentially is the differential of change in free energy on the right side and delta V dP on the left. What I'm permitted to do at this point is I'm permitted to integrate both sides because I've effectively separated the variables. All right, so on the right side, I'm going to integrate from delta G1 to delta G2. And since all I'm doing is integrating a differential, I just get the function inside the differential, evaluated according to the fundamental theorem of calculus. On the right side, I continue to have, I'm just going to keep this for now as the integral from P1 to P2 of delta V dP. And when I do this on the right side, at least, I just get delta G2 minus delta G1. Now, this 1, like we saw with pressure or temperature, indicates that this is delta G at pressure 1. Okay. This 2 here for delta G2 indicates this is the delta G at the higher or lower second pressure. Okay. And I'm going to continue to have this as the integral of P1 to P2 of delta V dP. All right, and that's just added on. And what I've done here is I've added the delta G1 at pressure 1 to the other side. And since normally what I'm dealing with is a Gibbs free energy at equilibrium, a standard free energy because it's much easier to deal with, I'm going to head and denote this as delta G standard with the little degree sign. But note that this can also just be a regular delta G at pressure 1 if you do know that. Okay. Now, this is the general form of the solution to that differential equation. Okay. However, for ideal gases, one thing we can say is essentially that the change in volume, we can actually just write as nRT over P. Okay. So for an ideal gas, I can substitute this delta V for this nRT over P and just plug that in for delta V and keep the dP. That's going to allow me to put this in terms of pressure, and I can just integrate both sides, or integrate this side, excuse me, with respect to pressure. So I get delta G2 is equal to delta G1 plus the integral from P1 to P2 of nRT over P times dP. Okay, when I integrate that, of course, I get this term, which is going to be the natural log of P2 over P1 times nRT. However, because pressure 1 is almost always, when you're doing this, at a standard pressure, the P1 you can also write as the standard pressure, and that's what's indicated here. So these are two equally valid forms of the same equation, and this is what you would do for ideal gases. Okay, if you had a different equation of state, you would use a different expression for V or delta V, in which case whatever's inside the integral is going to be very different. Okay. Regardless, delta G2 and delta G1, this component in both stay the same, but whatever this integral evaluates to can change depending on the gas model you're using. Now that's for ideal gases. Why do I have to use nRT over P as a substitute for V or delta V? The reason is because for ideal gases, and gases in general, not just ideal gases, van der Waals gases, Redlich-Kwong gases, and so forth, is that volume is a function of pressure. It's a very strong function of pressure, as we know. I can write the ideal gas equation as nRT over V, and then V is equal to nRT over P. So if I know the number of moles and the temperature, the volume pretty much specifies the pressure and vice versa. So they are functions of each other. However, if I move to solids and liquids, it turns out that volume is not really so much a function of pressure. They're more or less independent of one another. So if I know what the delta V is, you can sort of treat that as completely separate from pressure and not a function. So here's what I have from above. Delta G2 is equal, or minus delta G1 is equal to this integral that I had before, from P1 to P2 of delta V times dP. Now, we just said that delta V in the case of solids and liquids is not really a function of pressure. Well, if it's not a function of pressure, it's a constant, basically if you're considering that you're integrating with respect to pressure. So you can actually just pull this outside of the integral, and that's what I've done here in the second step. And then I have delta G2 minus delta G1 is equal to delta V times the integral of dP from P1 to P2. And obviously when you evaluate this integral of dP, that's just delta P. So that's what I have here. Delta G2 minus delta G1 is equal to delta V times delta P. And if you wanted to evaluate what this is, remember it's going to be V2 minus V1 for delta V, but since you're evaluating dP from P1 to P2, this is just P2 minus P1. Okay, so you take this, V2 minus V1 times the quantity P2 minus P1, and that has to equal delta G2 minus delta G1. So, in other words, if you actually wanted to go ahead and evaluate this for delta G2, remember that if you're doing this for a liquid or gas, or any of them really, but particularly for liquids and solids, volume 2 is known, volume 1 is known, pressure 1 is known, and if you want to get it at another pressure, then you just specify the pressure, so that's technically known. You should know delta G1, so all you have to do is find delta G2. That's your only unknown in the end. And then if you want to find that, you just add delta G1 to both sides, and you get that delta G2 is equal to delta G1 plus V2 minus V1, or just delta V if that's what you have, and then times P2 minus P1. And that would be how you isolate delta G2 if you know everything else and you have a liquid or solid. If you have a gas, you can't use that model. You have to use this, in which case you'd be adding nRT plus the natural log of P2 over P1 for an ideal gas. Okay? And so that is the quantification of the pressure dependence of free energy, that is Gibbs energy. Okay? In another video, we'll do an example with numbers so you can get a hang of this. We'll mainly deal with the gas side of it, though, so we'll be dealing with this equation right here. Okay, so hopefully that made sense. Make sure to join us for future videos. Like this video, subscribe to the channel for future videos and notifications. Thank you very much. Hope this helped.